Okay, in this section, we introduce the concept of Lagrangian string. Okay. Okay. This is the main concept of this chapter. As we have mentioned before, the classical string is not very appropriate to represent the deformation, especially when there is last rotation. Then classical string will give us wrong result. And then we started our journey to look for the appropriate measure for the deformation. Now we have already come to the last step of this journey. Okay, let me explain to you. N1 direction, N2 direction, we have dx1, dx2. We have already explained this picture in the last class. So I think you have already understand what they are. We have two material lines in the principal direction. Okay, and then of course we have rotation from N1, N2. We rotate the material line okay, we have rotation. Of course, we have also deformation too. Okay, we have rotation and deformation. The main, namely, the rotation are carried by this the angle difference between these two set of eigenvectors. 我用中文讲一遍哈，我们在一个广义的一个最广义的变形的过程里面呢，我们有变形也有旋转，对不对？然后旋转的部分呢，是体现在这个 eigenvector 的旋转，对不对？然后呢，它所那个需要的量啊，就是 r 了。所以呢，之前我有介绍过这个，对不对？这个 formula， 这个就是 rotation matrix 啊。然后呢，意思是说啊，这个 general 的一般的变形过程里面呢，我们已经把这个里面的旋转的成分给找出来了，它就是 r 矩阵 ，OK， 我们知道它旋转多少，就是 r 那么多 ，OK， let me explain to you. Given a general deformation, F. How large is the rigid rotation hidden inside R? See, hidden 啊，躲在里面。Okay, see, in a general deformation process, there are shape change, volume change, and also rotation. They mix up together. We don't know, at the first glance, we don't know how large is the rotation. And then after the computation, we get the matrix R. and then we know how large is the rotation. Okay. In the general deformation, how large is rigid loop? Let me check it, fix it. Okay. In a general deformation, F, how large is the rigid body rotation hidden inside, not out, inside F? Okay. In a deformation process, we have shape change, volume change, and also rotation. Okay. Mix up. Okay. All these mixed together. Okay. And then we don't know which part is which. Okay. But now, after the calculation, we know that rigid rotation is just the matrix R. Okay. Finally, we had we can have the method to find out the bad guy. Okay. Because all the troubles are induced by the rigid body rotation. The bad guy is the rigid body rotation. Now we know that who is the bad guy? The bad guy is R. Okay, R. How to compute? R is just U equal FTF, and then R is just F. And then U inverse. Okay, we first compute from F, compute U, and then U inverse, and then you get R. Okay, now we get the bad guy. This is the bad guy. Bad. Okay, very bad. So since it is a bad guy, we want to get it off. Okay, if we delete this part from F, then we get the pure deformation. Understand? This is the main idea. We first identify who is the bad guy. Now we have already done it. This is the bad guy. The second step is we want to cut it off. Okay, cut it out. And then the thing remains will be the pure deformation. Okay, see here. We have shape change and volume change and rotation. We want to cancel this part out. And then we get the real measure of deformations. Okay, this is the main idea. How to do it? It's easy, huh? It's easy. How to cancel? How to delete the rotation from F such that we can have a measure for the pure strain, okay, no rotation at all. How to do it？ 我们就是想怎么把这个 F 里面把这个 rotation 给删掉，那得到一个度量的方法来量这个真正的应变，然后就不会受到这个旋转，因为我们把它删掉了嘛，对不对 ？OK， this is easy. Let us tell you how to do it. F equal to RU, 对 ？And F equal to RU, so FT equal to UT RT, right? But UT is just U, right? And then RT multiplied by R, if we multiply RT by R, then they will cancel out to each other. Let us do it. Yes. Okay. And then because this is orthogonal, is equal I. Identity matrix, because R is orthogonal. Okay, so since this is the identity matrix, we have U, I, U, and then but we have U squared. Okay, actually, so this tells us that U squared is the matrix which have low deformation, low rotation at all. Low rotation. In U squared at all. Okay. Low rotation in U squared at all. So U squared is a quantity which contains low rigid body rotation at all. So this is the measure we want to have. Okay. Do you understand what I mean? Let me explain it in Chinese. Once again, 我们想要把这个 R 给删掉，因为 R 是旋转嘛，不想它出现在我们的变形里面。然后我们算一算这个 transpose， 对不对？这个转置以后呢，因为这个是对称矩阵，这个就变这个了。好了，然后我把这个乘上这个，就摆这边啦，这个摆这边，这个摆这边，对不对？然后呢，但是因为这个是正交矩阵。所以 RTR 呢就等于 I 啦，这个是因为它是正交矩阵，你们可以查查公数的书，所以就变成 I 矩阵，就是单位矩阵，单位矩阵呢就成其他的东西就不见了，就变成这个，所以这个里面呢就是已经没有 rotation 啦，没有 rotation 了，对不对？没有 rotation， 所以它就是一个很好的那个的那个什么呢？应变的度量的量，OK， so Okay, because this contains low rigid rotation, so it is a good quantity, okay, to stand for strain. Okay, this is a important concept here. 我用中文再讲一遍因为这个呢是没有那个钢体旋转所以这个量呢就是应变应变的一个很好的一个量，但是它有一个小缺点，是什么呢？应变就是说，当你没有变形的时候，我希望那个应变量是0嘛，这个不是，对，所以呢，我稍微还要修改 ，OK，but you still have a small defect here. defect. What is the defect? Okay, the defect is when there is no deformation at all. When there's no deformation, F equal I, right? Because dy equal dx. Okay, by this time, F equal I, and then what? And then F equal I, and then U square equal to FTF equal to I times I equal to I. It is good. It's not very good because now it is not equal 0 because we expect that a string will be 0 when there is no deformation. Okay, you say that it is good enough. Because now it is equal to an identity matrix, but somebody say that it is not good enough. I want to have 0 string for low deformation. So when there's low deformation, your string tensor equal to identity tensor. So it is not good, but not very good, not perfect. You know, let me say in Chinese 我们希望说这个作为一个应变矩阵的话，在没有变形的时候，这个应变矩阵要等于0，对不对？但是如果你用 u 平方来做你的应变矩阵的话，那你这边在没有变形的时候 ，f 等于 i，u 也等于 i， 就不等于0啦。所以没有变形的时候呢 ，u 矩阵并不是0。所以呢，这有个小小的瑕疵，那很容易了要克服这个小瑕疵很容易的，就把它减掉 i 就好了嘛，对不对？把 u 平方减掉 i 就好。Okay, to overcome this little defect, it is very easy. We just define our string by u squared minus I. Okay, we just delete the identity matrix from I, from u squared, and then we get the exact expression. Okay. Remedy. 补救的方法remedy. Okay, define the string as okay, this is the string we want. We define the string as what? As E. This we give it the name E. This is the string. It's 1/2. Okay, and then you don't ask me why there's 1/2. I have already explained this concept to you before. We have 1/2, of course, and then u squared minus I. It's clear. If we divide in this way, if there's no deformations, then u squared equal I minus I equals 0. And then, so when there's no deformations, then E equal to 0. Okay. So this is the string we want. Okay. This is the Lagrangian, a big name, Lagrange, 拉格朗日，对不对？当然是很伟大的名字哈。Lagrangian string, okay. Remember this name, Lagrangian string. Okay, this is the string we finally have. Okay, this string have a lot of merit. We will explain it later. OK， 这边暂停哈，好，就擦黑板好了。